In this screencast, we're going to look at the concept of average value. Before we do it, we'll just go back to first semester calculus and review the idea of average value in first semester calculus. The idea is if you have a function, f, from a to b, then if you want to find the average value of the function, you could think of this, suppose it was an anthill, and the ants have built a nice smooth top on the top. Remove the ants and then take the anthill and shake it. When you shake the anthill, the sand's going to level off, and you'll essentially be left with something where this area up here has replaced that area down there, and you're left with a certain height. So the area stays the same, but the height becomes flat. So there's a way to look at this. We're just trying to find area, and the area, when we have a flat top, is the height times the width. The width is b minus a. Whereas opposed to at the beginning, the area is integrated a to b f dx. So if you want to get the average value, just divide both sides by b minus a, and that's your formula, or integrate a to b f of x dx over b minus a. That is our formula for average value. That's going to generalize to higher dimensions as follows. Suppose that you take a three-dimensional, let's just take an ellipse, and above the ellipse we'll have something of varying height. So I believe this looks like the example from the first screencast where we took essentially the parabola 9 minus x squared minus y squared and cut the top of it, cut the top of the cylinder off of that. Here you could think of this as some kind of elliptical ant farm where they're now building things around an ellipse, and then if you take that thing and shake it, you're eventually going to end up with something, with a cylinder of constant height. And what's the height of that cylinder? Well, the idea is, again, we're getting area, and area can be found by taking the height of the cylinder and timesing it by the arc length, the arc length. That would be the length of this curve, s. Or you could just compute the line integral, f ds, which means if you want to get the height, it is 1 over s, integrate f ds. Well, the way you get arc length is you add up little bits of length. So essentially you're taking the function and integrating it and then repeating the integral but leaving the function out. That actually works up here as well. If you integrate the function and then remove the function, then the integral from a to b of dx is just b minus a. So this is our key idea. Average value is integrate the function and then divide by the same integral but leave out the function. This actually gets applied to things such as centroids. If you want to find the centroid of an arc, so say you've got a semicircle and you want to find where the centroid is, the centroid would be its center of mass, assuming the arc has the same density in it, probably somewhere in there. If you want to get the centroid, then the idea is find the average x values, so that means average the x values. Just replace f with x. If you want to find y bar, well then you find the average y value, and that'll give you y bar. And if you want to find the average z value, in this case there's no z direction, but if you go into 3D, it's the same idea. Find the average z value. And that is one key application, centroids. You use that in statics and lots of engineering classes. We're going to just look at an example that doesn't involve centroids, and we'll look at something like average temp. So suppose you know that the temperature at any point in space, you've got some kind of varying temperature area, and the temperature is x squared plus yz. And then you have something follow through a helical path. So cosine t, sine t, t. What is the average temperature encountered by the object as it passes through this temperature along this path? So as I move through space, where in the world, what's my average temperature? And let's just go once around the helix. Well, the idea is if you want average temperature, then you add up the temperatures and divide by the integral of the curve. Well, I need to go from 0 to 2 pi. I need the temperature, x. Well, here's the x value, so that's cosine squared t. That's this part, plus y. Well, y is sine t, and z is t. Now I need to multiply that by ds. To get ds, I need to calculate r prime. R prime is negative sine t, cosine t, t. And then I need the magnitude. So r prime in magnitude is sine squared plus cosine squared is 1 plus 1. That should be a 1, not a t, is root 2. So I multiply by root 2 dt. That right there is my ds. Then in the bottom I integrate 0 to 2 pi. ds is again root 2 dt. That would be the average temperature encountered by the particle as it flies through one loop. That ends the screen.